So welcome to Introduction to MPI, and thank you, Dr. Ludovic Capelli, for being our instructor, who's here all the way from Scotland, enjoying the Australian sun. Anyway, so thanks for coming, and thank you, Pascal, for getting the resources up and running for us. And thanks everyone for joining today. Before we launch in to a busy session, I'd like to acknowledge the traditional custodians and owners of the land on which we are sitting here at Pawsey, and that is the Whadjuk people of the Noongar Nation. I'd like to pay respect to their elders, past, present, and emerging, and extend that acknowledgement and respect to all First Nation peoples around Australia and around the world. And if you could put into the chat the lands from which you're dialing in on, that would be great. With that, I will turn it over to you. Thank you.
Right, thank you very much. Good morning, everybody. Good morning, everybody online. Before we begin again online, I do not see notifications straight away because I'm in presentation mode. So if you have any questions, make sure that you write a message on the chat. You don't be afraid to unmute yourself and ask the question directly. I'm more than happy to stop and re-explain something, reformulate or clarify. So feel free. Something else, at the end of every workshop, there's the post-workshop survey. And the two workshops you're going to see today, it's their first run. They have been designed for this event. So your feedback will be all the more useful and valuable to improve the other iterations in the future. So feel free, as I always say, positive and negative feedback equally welcome. The equally here is the keyword. So if you have any suggestions on how to improve something, yeah, we can get into the actual fun stuff, which is MPI, which you may have heard of. I believe anyone has heard of MPI before? Yes, Pascal. Yes, I believe you. Okay, so the content in this lecture Slack comes partly from John Urban, who's a professor at PSC, Edinburgh Supercomputing Centre, and a distinguished professor at CMP University. The slides I'm using are made using Beamer, and I use some sequence diagrams with a package I slightly extended, which is given here. When it comes to the license of these slides, all that means that basically you can do everything you want with the slides except for commercial use, or somehow changing the slides and making it look like I endorse the changes you made. And this final little note is to say that these slides are designed for live presentation, so they contain little text on it. They contain little text and explanations. Why? Because I'm doing the link with the presentation. If it was meant to be studied on your own, I would have put a lot of text, which would have made it a much less interesting presentation line. So that's why I chose a slide here. Anyway, what I call the moment of truth is we're going to see if things work. If they don't, they won't work now, so that we can know it now and can fix it, and then you're good to go for the rest of the day. So you can try to log on the AWS node, which indeed Pascal very kindly set everything up for us. Took quite some time, I believe. It's been quite short now, so thank you very much, Pascal, for doing all that. I believe this is the IP address, the updated IP address, up-to-date IP address. So you can try to SSH on that AWS node using the credentials that you will have taken from the spreadsheet online. And then you can try to clone the repository given underneath. Let's see if everybody can log in and clone the repo. If you have any problem, it's the perfect time to say it. Right? Okay. You will see in the repository you just cloned that you have multiple directories, each numbered. They each represent a technique or a concept that we're going to illustrate and practice on. If you were here on Friday, you will see that it's exactly the same structure. So is the actual first attempt. So this is the first exercise. There's nothing to do other than for you to compile it and to run it. Don't worry if you don't know what this command means yet. We're going to see that. But this exercise is just to check that the whole software stack works for you. So going to the repository, you will see that there are two folders there, C and F, because exercises are available in both C and Fortran, as always, Fortran 2008 even. So take your pick and then go into the first directory and try to make it. Normally it works like a charm. I tried again this morning, Pascal set everything up. And then you can try to run the binary that you're going to produce, and normally you should get a message. Again, that's a very quick one. Normally we should have thumbs up in 10 seconds. If not, we'll fix this.
Yep, worked for me.
Yep, and we're getting some, we got one thumbs up online. Any more online with thumbs up?
So the Fortran.
I know I went C this time.
Oh, you went C. Okay.
Yes. Once bitten.
Fortran reference.
Yeah, once bitten.
I can try the Fortran in the background if you need.
Okay, yeah, just to check that the Make5, for example, I updated the compiler, the wrapper behind the scenes.
I last used C about 35 years ago.
Jesus.
And I can probably still use it. Oh, I didn't bring my books.
It's on. Are you good? You're on?
Almost there. Need to catch up a little bit, but should be fine.
Okay, online, no messages of errors or anything?
No, looks
Okay,
like.
cool. Sounds like we can get into it now. Cool, so we're all set up and ready to do the break. So, as always, let's see what we're going to talk about and why we're going to talk about it. If you look at HPC node, HPC node on Zetonix, on the HPC cluster or supercomputer you want, you will see that you can find on a single node, a single machine, right? You can find over 100 cores. 128 is not rare these days. It's pretty common, 64, 128 or more. And you can even have typically hundreds of gigabytes of RAM. So 128, 256, 512. It exists a few nodes with 700 or even over a terabyte of RAM. But despite having that much power and memory, it can still be insufficient, because sometimes you may want to have even more memory or even more compute power. The problem with memory is when you don't have enough memory, you just cannot run the application unless you go to other types of processing, which we can call out-of-core computation, which is very interesting, but something different. And if you need more compute power, typically, without getting more compute power, you can still run your application, just that it will take longer than you would like, or can afford to wait, or pay. So, by definition, multiple nodes, so multiple physical machines, do not physically share memory. So we cannot have them exchange data the same way we were doing in shared memory programming. Instead, we will have somehow to go through the network. And one of the approaches to have multiple machines communicate is for them to somehow put data into a message and then send this message over the entire network. So this is what we call, well, there has been multiple attempts at this. And exactly like in OpenMP, where there have been many attempts to try to design something for shared memory programming that's been the same for this approach of, okay, let's put some data in the message, send this message of the network, and efforts have been conducted and led to the emergence of the MPI, which is the message passing interface. So that's exactly what it is, an interface. It's basically in its raw form, it's a long PDF, but I mentioned that in the next slide. MPI is not a programming language, it's not a compiler, it's not a framework, it's a standard. It's a long PDF file. OpenMP is approximately 600-700 pages, MPI is over 1,000 pages. So these are big standards, which are behind the scenes implemented by vendors, IBM, Cray, so on, Intel, and so on and so on. The MPI Forum is the organization, the consortium behind the scenes that decides what to put in the standard, which then gets implemented by the vendors. So the MPI version 4.1 we voted on it last month, and it has been around for 30 years. MPI has been around for 30 years. More or less at the same time as OpenMP, so these two have been there for a long time. So they went through a lot of optimizations, which is why in HPC it's hard to get away from them because they're very well optimized. So how does it actually work? We're going to talk about two terms first to clarify something. We're going to talk about processes, but we also talked about threads with OpenMP, with shared memory programming. So let's first clarify what these two are. A process is an instance of a program. That's it. If you open your task manager, you will see many processes. You will have your browser, you will have your Word document, you will have your teams, and so on. A thread is a list of instructions that is inside a process. Okay? If we look at the OpenMP program that we were writing on Friday, we had a single process with a main thread, and we were spawning threads inside that process. Okay? Everything was still inside one process. With MPI, what we're going to do is we start with a process, but actually we won't have a single process. We'll have many processes, each of which can have threads. Okay, can have even different number of threads if you want. The whole point of this is these different processes, these different instances of my program, I can put them on different machines, which I can't do if I have just one process. Because the operating system will say, well, where do you want to run the process on this machine? Okay, the operating system on that machine will run this process, but it means it cannot be run there. If you want to run it there, you need another process to be on there, which is what we're going to do with MPI. We're going to have multiple processes which we can put on the same machine if we want, or on different machines. And that's we are enabled to do this because these processes communicate with these messages. If they are on the same node, if they physically share memory, they can exchange data the same way threads do, just by directly accessing each other's memory. However, if they are on different machines, behind the scenes, MPI will issue the network communications needed to pass this message between the two machines, finding the right IP address of the machine, the right port, and so on and so on. All this is taken care of for you by MPI behind the scenes. So it's very neat. But to have all this made for you, we're going to have to go through 3 steps. The first one is that every MPI program will need to call something called the parallel launcher. Why? Because normally, when you launch a program, I'll explain that again in a second. When you launch your program, just type / and something. So that's almost one instance of your program, one process. Here we're trying to run multiple processes. So somehow we'll need to launch our program in a slightly different way. Second, you'll need to do a call to MPI init. I'll come back on this one in a few seconds. And we need to call MPI finalize at the very end. So inside our program, we call MPI init at the very start, MPI finalize at the very end, and we run our program using these comments there. Now I'm going to explain everything step by step, so don't worry. First step, as I said, if you run your program using this, it's perfectly valid, it's perfectly correct, but you will have only one process. So one MPI process, not more than one. That's what's going to happen. Now, since we need to launch multiple instances, you could do that manually, almost equivalent to as if you were opening multiple terminals, and in each terminal calling that /. Okay? But the commands we're going to use to do that for us take care of more than just spawning the instances. So it's going, of course, to actually spawn the instances, but it will also somehow provide all the MPI processes with information about where to find each other. Oh, there's an MPI process on the machine with IP 2425, and then there's an MPI process on the other machine with IP 6424. The port on this one is 2950, the port on this one is 5200. All this is taken care of by just the MPI run command. Okay? So if you try to launch a program this way, you have a single instance. Now you know it. Second part, the second aspect we need to take care of, initialization. This is where, now that we have multiple processes, they are not connected yet. That's why when you run the example, the preamble example, the message you were having was each MPI process printing, I don't know where the other MPI processes are. Why? Because they are not connected yet. Your instances have received information about where they can find other MPI processes. But so far, the communication channels have not been established. All this is going to be taken care of for you by the MPI routine that we will call. Okay? It will even do something better. It will create what we call a communicator, which is where communications can take place. By default, it creates one that is called MPI com world or MPI communicator world. It contains all your MPI processes. Even if you spawn 2 million MPI processes, it will still contain all of them. When we will see a bit later through this workshop, what we call collective operations, where all MPI processes communicate and participate and contribute, we'll use MPI com world. Now, there's also something else that MPI init does for you, which is it assigns ranks. Because when you have 10 MPI processes, somehow at some point you must be able to identify them. So we need someone to be the rank 0, someone to be the rank 1, 2, 3, and so on. MPI init will do this for you. Okay? So this is what it looks like. It's the only function really that will have a different signature in C and Fortran. In C, you can pass your argc and argb from the main function. You just pass a pointer on each, done. In Fortran, there's nothing. In Fortran 2008, the error here is optional because the way it works is all MPI routines, all of them, we're going to exclude the 2 exceptions. Out of 400, we can say all. Return an integer in C, which is going to be the error code. In Fortran, it has been designed differently, and the error code is not returned as a written value, but it's filled into an out parameter, which has been made optional in Fortran 2008. Okay? So regardless of the programming language that you use, this is what you need to call before calling any other MPI routine. You call your MPI init, and then you're good to go. Then, once you have the MPI init, you call all the MPI routines you want. You have fun with distribute, because that's what we're talking about now. Distributed memory. With OpenMP, shared memory. Same node, they can physically access each other's memory. With MPI, distributed memory, because now we can put them on the same node or different nodes. So we can have 200 gigabytes of RAM from this node, 200 gigabytes of RAM from that node, and now we have a distributed memory. Step 3 to be done with our program, and then we can have our first exercise. We need to call MPI finalize, which I'm going to show in a couple of slides, because we need to wait for any communications that we started to actually complete and finish. MPI finalize will take care of this for us. It will also do other things such as cleaning jobs if you want. The communication channels that I mentioned were created in MPI init. They somehow need to be destroyed, all the resources deallocated, freed, and so on. MPI finalize will take care of this for us. And this time, whether it's Fortran or C, there's nothing in C and nothing in Fortran, except, as always, this error code if you want it. Okay? So now that you have seen MPI init, MPI finalize, and the run command, you can try to have your first go at the first exercise. There's something I didn't think to put in the slides, which is when you type MPI run, you need to pass one argument, which is going to be the number of processes you want to run. So when you type MPI run, then you pass -n for the number, and then the number of MPI processes you want to run. 4, 10, 54, and then you just pass your binary. So have fun at this. I will show the command on the screen. And if you have any problem, feel free to say yes. Normally there's a sneaky thing that you may have a problem doing. Let's see. So in Fortran, MPI _F8 tells Fortran that is going to load all the Fortran 2008 related libraries. If we have a more comprehensive answer from a Fortran expert in the room, feel free to step in. Because if I just load MPI directly in Fortran, it will not load the Fortran 2008 binding, which means that the error parameter is no longer optional, but it's not compulsory, plus many other things. If you're learning MPI from Fortran, go to the Fortran 2008. Please don't use Fortran 19. So far, so good for the F90, yes. Oh, yes, wait. Yes, I really made sure that there would be no confusion with MPI not being a programming language, not being a compiler, not being anything but a standard. What we're compiling our program with is MPI-CC for C, or MPI-F19 if we were to use Fortran 90, Fortran 90, or MPI-Fort if we're using the 2008. These are not compilers. These are what's called wrappers. Basically, you can see them as a little script, which behind the scenes calls whichever compiler you already have installed, GCC, Intel, Cray, and so on. And they just pass a long list of libraries to load and arguments and environment variables so that the MPI side of things is properly loaded. So there's no magic. MPI-CC or MPI-Fort is nothing else than using your compiler and passing a lot of arguments to it. Okay? But I know that at first it can be a bit daunting. Okay, that's the end of the first 5 minutes. So let's have a look at the different exercises. Now let's do it like that. So, source. So what did you do in this program? So let's do it step by step. In MPI programs, before we start thinking about executing our program and so on, we need inside our program to make sure that everything is to be set up when we launch it, when we launch multiple instances of it. That's really the hard part, thinking about how it's launched, because it's really an entirely different what we call paradigm. It's an entirely different way of programming and approaching your programs. So the first step is when we're going to have our multiple instances, when we'll launch them later, we need them to somehow coordinate and link to each other. And that is done through the MPI init. There's some delay. Is someone using all the CPU on the machine?
Put in a million.
So we're in C, so we're going to pass these two arguments. you could afford to pass null if you want, but it's good practice. I won't get into the details, but it's good practice to pass RC and RV. In Fortran, you call and you pass no arguments, it's entirely fine. So as soon as I call MPI init, then I can use all the MPI routines I want, everything we're going to learn this morning, later on. And at the very end of my program, to finalize my program, I need to call MPI finalize. All MPI functions have this same format, MPI in capital letters, underscore, and then what comes next with the first letter being capitalized. So finalize, like this. So now in our program, we initialized it and we finalized it. So this is now a valid MPI program. Now we're going to launch it, not like this, because that's just going to spawn one program. We need to run multiple instances. So we need to use MPI run -n4. Okay. You can run one. You can even run one instance if you want from here. That's entirely fine and correct. But here, let's try to run with more than one. Okay, so now we have 4 MPI processes who don't know each other yet, but we still have 4 MPI processes. No, sorry. They are connected to each other, but we haven't seen it yet. How to get an MPI process to get its own rank and to ask how many MPI processes there are in total. We're going to learn that right now. But now, does this make sense to everybody? Yes? Okay, again, yeah. That's really the challenging part. It's a totally different starting point from normally everything you've seen so far. Even OpenMP is fine because OpenMP, you're inside your process and you just spawn more threads. Now we have multiple processes next to each other.
Can I ask a question? Yes. Can you run MPI run -4 ls? ls is a simple command. It has no knowledge of MPI.
I don't think it's going to work as is. Let's see.
Just ls, and then we'll run 4. But
okay.
There's no infrastructure in the command. It's just it spawns processes. These processes can never do anything beyond what they do. They're truly independent.
Yeah. So all these are.
There you go.
All these are processes. Well, I cannot see much. Oh yeah, because I'm so zoomed in. All these are processes. That's typically what you have on your computer all the time. So your operating system runs many things behind the scenes. All these are processes. Open your task manager, you will see. So different instances of sometimes different programs, or the same program. MPI, you can see it. I thought of this analogy a few weeks ago. You can see it as your actual body cells. That's how your body cells work. Whether it's a cell that is now in your nail, or in your eye, or in your skin, it's the same cell with the same DNA at the start. Here, our MPI programs all have the same source code, the very same source code, but we will spawn multiple of them, many of them, and we can get them to specialize to do certain actions or certain other actions the same way your body cells specialize to become a nail cell or a skin cell or an eye cell or an elbow cell. So I really think this. That's really a DNA approach of things. I just like it. Anyway, makes sense to everybody? Again, quick thumbs up in the chat so we can see everything is fine, and then we get to learn the interesting stuff. Yes. Okay. Perfect.